Hi everyone, my name is Mike, and today I'd like to talk to you about detection engineering. And detection engineering is kind of an interesting field of cybersecurity, and it's about trying to find detections, trying to find intrusions, and today I'd like to discuss some of the interesting techniques and problems that we encounter in detection engineering, and try and get everyone to think about how they can write better detections and work through some examples. So this workshop will discuss detection engineering with Velociraptor. Now, Velociraptor, if you haven't heard, is an advanced digital forensics and endpoint monitoring solution, an open source solution, but that's not really the only detection solution available out there, of course. And today we're going to talk about detection engineering in a more general way. We're just going to show it in Velociraptor as an example of a platform that is actually pretty good at writing detections. But I think a lot of the lessons that we learned today could be used, in other systems as well. So we're going to point out how some other systems, behave as well. But the important thing about today is to try and figure out, the way of thinking about how to write better detection. And in particular, we're going to talk about Sigma as a sort of a detection standard and how to write Sigma rules in order to try and write better detections. Okay, so we're going to do a very hands-on workshop today. So just to start off, we're going to download Velociraptor and just install it. That should only take 5 minutes because we don't have a lot of time with all the exercises that we're doing, but it's going to be kind of a hands-on workshop. So I'm just going to go through and download Velociraptor, and you can just download it from the GitHub site. You can Google for it or whatever. And down here we have our releases. If you just Google for it, you can find the website here. Here is our website, and over here we have the downloads page. And I'm on a Windows machine, so we would recommend use Windows for this workshop. It's going to be Windows centric, so I'm just going to download this latest release at the moment. And if you're doing this later, watching this video later, there might be a more recent release, so just grab the latest one, and that just basically downloaded an executable. Now, Velociraptor is just a single executable, and everything is included in that one executable, a server or a client. So we're just going to spin it up real quick so that we can get started with the workshop. So we're just going to have a look at our downloads directory, and it just comes as one single binary, and all we have to do is we just type Velociraptor GUI, and that will just set up like a small demo environment locally, and spin up a browser and spin up the browser and a client and a server that talks to it. So it creates a self-signed certificate just for this demonstration purposes, and it's connected to the local host. So we just click through this warning, and that's all it is. Essentially, like instant Velociraptor, we have it running. It's actually a fully functional Velociraptor deployment, and we have one client attached to it. So there's one client and one server. So let's have a look at. Okay, so we just ran this. If we wanted a more permanent data store, we can have it, but at the moment for this workshop, we're just going to use the defaults, which just uses the data store in a temp directory. So this is the main Velociraptor dashboard, the main welcome screen, and that just gets us started. So I'm not going to talk too much about Velociraptor today, because we're going to really focus on detection engineering and writing detection rules. So it's just a tool for now. So why do we want to write detections? So as you know, attackers are getting faster and quicker and better at running through their attacks, right? So, whereas in the old days we had, enough time to review logs manually and try and detect intrusions manually, these days that's just not possible because attackers are very quick, and we need to stop them quickly before they propagate through the network. So we really need automation, and detection engineering is really all about making these detections quickly and finding malicious action quickly and with reduced false positives, right? So we don't want to we want our SOC to have very targeted alerts so that they don't have to spend time chasing a lot of malicious activity, false positives, right? So detection, so we know what we wanted to do, more detection, but now why do we have this word detection engineering? So where does the engineering come into it? And this term, detection engineering, is supposed to kind of bring this idea that detection is more than just writing a query into your SIEM or something like that. It's a process where we build a systemic process to build and engineer a better process for detection, improve our detections over time. So instead of just writing random queries and trying to detect random attacks, it's about being systemic and creating a process to follow as we go through, being iterative so that each time we go through the process, we are getting better, having less false positives, and finally having a resilient process that we can test and make sure that we don't suddenly break our ability without realizing to detect. For example, like we have event sources, we have to build tests around do we still get forwarding of those events, or suddenly for whatever reason the sensors have gone offline but nobody realizes, so we can build tests into the system to figure it out. And the word engineering brings design into the idea. Like we have to actually consciously think about and design a system to improve this detection. So really the goal is to maximize the probability of detection, to write these rules that maximize it. So it's all about thinking about how can we build better detections, how can we adapt those detections to evolve with the new threats that are coming onto the field, and how to make sure that the lights are still on, right? That we are still seeing those events and the detection is still working. So it's it's kind of like trying to bring this kind of idea of deliberate engineering process into it. So here's a picture here from where does detection engineering fit in the in the entire incident response process. And it's got a whole bunch of kind of analysis here where people see detection engineering working in terms of before the investigation, feeding data into the investigation, receiving data from threat research, and so on. So we actually have detection engineering is like its own discipline where people can specialize. So this is kind of where the detection engineering role comes from. So it's not just a being able to write queries into a SIEM and just looking at data or reviewing logs manually. It's more really emphasis on the engineering side and the feedback cycle. How can we make this better? How can we improve the process? Okay, so let's have a look at what is a detection pipeline in a typical SIEM, right? So we have a whole bunch of different event sources, right? So for example, we might have syslog coming in from some Unix systems. We might have Windows event logs coming in from some systems, or maybe an EDR producing some logs or whatever. So different products produce different types of data sources. And then usually what happens is those events are forwarded from the endpoint or wherever they are generated, forwarded to a central sort of data lake type of setup, a database or something like that. And by forwarding these events, from the original data source, they normally need to go inside some kind of database. So we need to kind of coalesce that data into a schema, because it has to go into a structured data store. And then at this point, we may do some data enrichment. We might go to virus.org, get some hashes, enrich with some other data, whatever, different things, GeoIP location, that kind of thing. And then at some point, we are going to basically query that data. And by querying it, we are querying it for the purpose of trying to find anomalies to get a detection, right? So a detection would be, in this case, would be a kind of query that we make against the data backend that would reveal anomalous behavior or suspicious behavior that we might want to look at in more detail. And so, when you have a whole bunch of infrastructure in a sort of, in a normal, an average organization, then you have all kinds of different event logs, event sources, data sources, and all kinds of systems that are stored in there. And each system might have different kinds of detection technology that you can query on. And so, it's kind of a mess, because you end up with like a detections are written specifically for the different systems. You have a detection for a syslog server, you got a detection for Windows event logs, you got a detection against EDR logs, whatever, firewall logs, these kind of things. So proxy logs. So then it's kind of hard to get a handle of what the detections are, the different systems, different schemas, and it's a big job, right? So this is kind of a pipeline. You get the data. Data is normalized into a certain particular schema, and then transported, stored, and detected. So that's kind of the pipeline that most people are familiar with. So for this workshop, we're going to look at just one single attack, actually. And so what we're going to do is we're going to think about how can we detect this very common, very simple attack. Like, we're not going to do some exotic, esoteric attacks here. This is very bread and butter attack. And we're just going to look at how could we detect that in a more robust way. So the attack that we're going to work with today would be this PsExec attack. It's a very well-known vector, and it's very, a lot of people are very familiar with it. PsExec is a very common tool that people use to be able to laterally move across the network from one host to another host. It's a sys internal tool. It's made by Microsoft, and so it's actually signed and trusted and all this sort of stuff, but it's commonly misused by attackers. So let's just, to prepare ourselves, we're going to download it from Microsoft. So we're just going to download it, and then we're just going to go over here, open another, okay, and just going to download it. Okay, and so so this is the tool. If we just look at it with Explorer, and right click on it, look at the properties, and you can see that it's actually digitally signed by Microsoft, so it's actually kind of trusted, and it's a fairly common tool. It's used by sysadmins as well, so it's actually pretty common tool, but it's actually used to laterally move across the network. So before we start, what we're going to do is we're going to install Sysmon. So Sysmon is a tool that is used to monitor system activity. It's a very common tool, but we're going to use that to look at some of the detections, some of the event sources that happen on the network. And Velociraptor actually has a way of installing Sysmon on the endpoint by itself, so it's built in, using this Windows sysinternal Sysmon install artifact. So let's use that, and we can just install it. So to do that, we will go to our endpoint, and what we're going to do is on the left hand side we're going to go to client. We're going to collect an artifact because we're going to install sysmon on this endpoint, which is really the same server because we are using the client is installed locally on this machine. So we're going to start a new collection. We're going to search for sysmon. Okay, and then we have an artifact called Windows sysinternal sysmon install, and that artifact will actually push the binary to the endpoint and a very common config file, and just launch it, right? So it's just going to install sysmon on the endpoint. It's going to take no time at all, pretty much. And as soon as that happens, you will start to see events being fed into the event viewer, right? So if we open up the event viewer, there we go, and we'll start application logs, Microsoft, Windows, sysmon, okay, and then sysmon here, operational, and then we're going to find some, a whole bunch of logs here generated by sysmon. And this is going to be our event sources, which we'll look at in this part of the workshop. So just to start off with, I'm just going to clear this log just to make sure that we've got a small amount of logs to look at, so we can just examine, what kind of events that are actually generated during an attack. So let's go back to our slides there. Okay, so we've installed sysmon. That's great. So now we're going to do an attack. So what sysmon does, first of all, we need to understand exactly what PsExec does in order to run, and how does it actually work? What is this attack, or how does this work? And people normally use PsExec to get a remote shell on another machine. And in this case, with the -s flag, they actually get a system level shell, so it's like a privilege escalation type of attack. And so what we're going to do is we're going to just do this one attack throughout the whole workshop, and we're just going to try and figure out how to detect it. So let's try and do this attack. What does it look like? So okay, let's have a look at the. Yep, I'm going to go over here. And if you do try this later, we're going to use, this is your host name of this machine, which actually you can find by looking at the Velociraptor console, right? Because this will be your host name here. So it's the same. This is the host name, right? So okay, so we're going to launch this attack against this system, and this host name is going to be different depending on which host you have. It's just your local host name. Okay, and then let's run it, and you can see that it opens up a shell, and if I type who am I here, it shows me that I'm running as system. So this is like a privilege escalation. So let's have a look at the event logs and see, let's do a refresh, see all the different kinds of events that happened. That happened during this attack, to understand what is actually happening. Okay, so the first one is an event 1, which is process execution, process create, and we can see that we started this program. We can see this is the information about this binary and so forth, and parent image was command. So the first step, we're executing the PsExec binary, right? And this is our command line, right? So this is just what I typed before. So the next step that happens, we can see that clearly, a registry value will set. So that means that this is the process. PsExec has set a registry value, and this is the value, hatch key users. software sysinternal PsExec EULA accepted. So it turns out that PsExec sets this or checks this value to make sure that the end user legal agreement, the EULA, was accepted. But for us, we can use that registry access as a detection, and it also leaves the key behind, so we can actually see when it was last run and things like that. Okay, so that's kind of an interesting one. The next thing, we can see that it creates a file, right? And it creates a file, it writes it to see Windows PsExec SVC. Okay, so that's the service component of PsExec. And the way it works is it actually writes a file in the Windows directory, right? And then it sets it to be a service. And you can see that this service controller sets some service related registry keys here, like the start key and so on. So we can already see that there is a service here called PsExec SVC that is added to the system, a new service. And this service is written into the registry. Okay, so it sets up the service. And then we have a new process created where this PsExec SVC here is started. But if you look at the parent process that created it, it's the service control manager, right? And the service control manager is running the system. So that is how we get the system shell, because the service control manager is starting this process for us and creating a service. Then we have some other stuff happening, some DNS and other things, but then we get a shell, right? We have another process created, who am I? The command prompt is launched by this service, and that's how we actually get to see that command prompt launch. And then we run who am I in there and so on. So, and then we terminate it and it's exited. So this is the steps of the attack. The attack is basically, let's revise it in the slides. Okay, so when we start off, what we see, the first step is we see an execution here where we are running a command, right? Process create. Okay, and normally when we want to do PsExec across the network, this part will be done on the attacker's machine, because the attacker starts the PsExec process. Then the next thing that we do is the registry value is set, again on the attacker's machine. Then over RPC, we create a file on the remote system. And so we can copy it over RPC to the target system. Okay, so that's when we create the Windows file, PsExec in the Windows system. And then we install a new service. We've seen that. So registry keys are set in the registry for the new service. And then the new service is started with the service control manager. So that's how we get to be anti-user system. Okay, so let's try and collect some of these event logs. Okay, so we try and look at those. So we've looked at them in the event viewer, which is kind of nice, but in practice, those events will be forwarded to the SIEM, and so we will, basically receive them in the SIEM in like, raw data format. And so we're going to simulate that by actually collecting them with Velociraptor, and this is a fairly common thing to do even in just, when we're doing incident response, is to just collect some of the event logs, right, from the endpoint. So we have this artifact here, Windows event logs EVTX. We're just going to grab the sysmon event logs. And what this artifact does is it actually just parses the event log and then returns them to the server. So we're going to collect this, new collection, evtx. Okay, so not the hunter, just the normal evtx, and configure parameters. And all it does is it just passes the event logs and brings them back. So we don't want to get all the event logs. We just want to get the syspawn one, right? So I'm just going to go super lazy, just syspawn, right? And we can also filter it by, you know, start age, PSS, and all this sort of stuff. But because I cleared the logs, I know there's not too many. So I'm just gonna grab it. And this is basically what we would do, you know, in a typical SIEM system, is just collect the logs and forward them. So let's have a look at what those logs look like. Okay, so if we look at the results, then we will see the different types of logs that are returned, right? So if we look at this row JSON, then we will see the row like event. And so you can see that's the event data. Okay, there's a message, some time creator, channel, all this kind of stuff here, right? But the way that event logs look like generally is you have the system part, which has fixed fields, so they don't change. For all events, they have the same. And here's where we find, you know, the time and you know, process ID and other things, and the event, you know, ID and things like that. But then there is this event data part, which varies depending on the different types of events. So different events will have different fields here depending on, you know, what the event is, the event ID is. And then there's a message, which would be like a formatted version of that. So we're not going to worry too much about the details, but we can see that we have the system and we have event data and so on. So let's go back to the slides here. There's the slide. Yeah. So we collected these event logs. That's great. And you can see that there's different parts. And so, you know, we can actually reference each of those parts, you know, in a particular way. Right. So you can see, we'll go back to these ones in a minute, but just wanted to show you the different kinds of fields that we have here. Okay. Now let's collect the same thing again, but using the elastic event log sysmon. So the thing that we collected before basically just parse the log in just a normal way, just exactly how they are, and just return them as, you know, more or less JSON objects in pretty much exactly how they look like on the system, right? So we can actually compare this with the event viewer. It looks pretty much the same. But a lot of systems don't really just forward the exact same logs, right? They need to sometimes enrich those and, you know, massage the data into a particular kind of schema so that they can be stored in a database, that kind of thing. So, we have this elastic common schema. It's a very commonly used schema. It's just an example of a system that forwards logs and does this normalization, data normalization into a particular schema. And this is a part of the ELK platform, Elastic Kibana type platform, and they have published a particular schema called Elastic Common Schema. So we can collect the same thing, and if we search for ECS, then we'll look for Elastic Sysmon, right? So this is the ECS schema. And this does exactly the same thing, except that it normalizes the data into this kind of schema and also enriches it and other things like that. And so this is basically the same thing. We just collect it as it is. It's the same thing, but the data looks a little bit different because it's been normalized into a different data shape. So if we have a look at the raw data from this one, and you can see that it's actually got these extra fields, and you know, it's like normalized, it's got some modules. So if you were using something like Elastic, for example, then you would get the data would look like this, right? It would just be normalized like that. And then you have like this field called winlog and API and channel, and then the event data looks like this. And then here is, you know, the actual like raw event data just gets plonked into here, but you can see that there's different kinds of fields here, and there's different types of, you know, normalizations that are happening here based on the original data. All right, so that's now we've collected the same data, but the point is that they have different shape. This data looks different from the other data. They have different fields, they have different nesting, and it looks a bit different. So let's try now and write a detection around this. So we're going to do the same thing, but I'm just showing you here that you have to access them in a slightly different way. So let's detect this attack, right? So we have to find some aspect around this attack that we would like to detect. So we're going to write a detection, and essentially what is a detection? A detection just basically is like a match or a grep on the event log. So we're going to pass all the event logs on, and we're going to try and find an event log that matches a particular criteria or filters. We can filter them by this criteria, and if any of the events matches this criteria, then we call this a hit, right? So in this case, what we're going to look for is spawning of PsExec service. All right, so it's called PsExec SVC, and then we are going to filter it by adding a where clause to isolate the attack. Okay, so this is actually pretty easy to do, but we'll go back to those first slides. So what we're going to look at is this kind of look, right? So we're going to start off by trying to identify the field that has a PsExec svc.exe, right? So this basically will match whenever a process starts with this name. This is a pretty unique name, and you know, if a process starts with this name, bad news, right? So we will just want to detect it. But how do we get into it? You can see that at the top level we have event data, then we'll have a dot, and then we'll have an image. So let's do that. We'll go back to our Velociraptor, but what we're going to do now is just look at so we have these two collections, right? The first collection is just the straight out event logs, right? So let's go there, and what we can do here is modify. This is a notebook, which is like an interactive way of writing queries. So we can write a query against the data. So this query, this is the default query, just shows the fields, the first 50 records. So we're just going to change this. We're going to add a where, right? And here, let's go back to the raw data. So it's going to be event data dot image. Okay, so event data dot image, and then this is a regular expression match, right? And it's going to be PsExec svc.exe, right? So that's our PsExec service, and okay, and then when we filter the rows, we will find one hit. And you know, we can make it a little bit more robust, right? Because we can also look in the slides, we are also checking for event ID 1, right? So we can also do like system dot event ID dot value equals 1. Right, so that chooses that as well. It doesn't matter, right? It's just a more specific filter. Let me just clear a lot of these fields. I'm just going to show the system and the event data. Okay, and so this is basically the events that I'm going to look at, right? So you can imagine that now if I ran this against an event log with lots and lots of different events, then it's pretty specific. It's a filter. I've written a filter that will detect whenever this PsExec ran, and that's a detection. If that happens, then I know this happened. This PsExec ran. That's that's what a detection is. That's all it is. It's just a filter against all the events, right? That means something. So that's really great. So this is the first collection. That's awesome. But of course we cannot use the same query for the second one because the fields are all in different places. So if we go back to the SIEMs example, same kind of idea, right? If we look at our row event again, then we're going to look for a win log event data. It's going to be win log event data image, right? That's going to be the name of the image, right? So the same things, but it's the same but different, right? So we go where winlog dot event data dot image matches PsExec dot exe, right? Okay, so it's the same thing but different field, and we're gonna need to look for, it's gonna be a process type start, event type start, event category process, right? If we wanted to make it, a bit more specific, event category equals start. Oh, let's undo that. Go back. Take a look. Event category process, event type start. Okay, go back. Oop. What was it now? Event category. Manage it. Anyway, so it's a little bit more specific. So we're only going to get like process start events instead of other kinds of events or whatever. But it really doesn't matter because most of the time the image is going to be the same. But anyway, you can click on this to reformat it a little bit nicer. So here we have one query. That's great. And then here, we just format that again. We have the second query, but you see that it looks very different. And so this is really this exercise really explains how the shape of the data can actually change the way that we query it, right? So if we were to design a detection around this system, then it really depends on how we are collecting the data, where it's coming from, and and how we're storing it, the normalization that's happening to the data. Where does it, where does it go into the database, the type of fields and so forth. So it looks very different. So it makes it really difficult for us to share it, right? To share the system, because to share this detection. If I wrote a detection, and and then I had a colleague in another company, perhaps they're using Elastic, and we're using Microsoft log forwarding or whatever, which has the same kind of structure. Then we basically can't really share it because the different fields they mean different things, and so this has always been a problem with sharing detections or with the community. How do we interchange it? And the other problems that could happen is there's different things that could go wrong. For example, like if I try to share this detection, well, obviously, it's using SIEMs, so SIEMs has to be installed, right? But also, SIEMs has a configuration. What kind of files, what kind of events does it look for? What kind of exclusion rules? There's lots of different kinds of SIEMs configuration, and you may or may not actually even get to that event source at all. We don't know. But also, if it's even for other log sources that are not SIEMs, they may actually collect these event logs, but different. It looks different because there's different configuration. This is an example where we can see here command line process auditing, which is a particular event ID 4688, which basically tells you it's like a process execution event from Windows itself. So one of the fields is the command line, process command line. So you might be logging and forwarding event ID 4688, but it turns out that this command line, which is kind of a really important field, is not actually on by default, and you need to enable a policy setting to actually get it. So it means that if I write a detection that looks for this particular, that uses this field in the detection, and then I try to interchange it with someone else, and they didn't have this policy configured, then they will think that they're detecting this, but they won't, because we're not even looking at that field. That field is missing and we'll never detect it. So it could lead to problems with like false negatives, where we actually miss something because of configuration problems, right? The configuration is not real. So as a detection engineer, we need to know what the limitations are of the event source, you know, where these events are coming from, and how to check for that, and make sure that our systems actually can, you know, are actually relying on these fields that are actually present and collected. So these are kind of an interesting thing. Okay, let's go back. Okay, so full screen. Yeah, so we'll come back to this, and also the data shape is different, which we mentioned. So we'll come back to this in the next section and see what we can do about this. But these are some of the problems that might happen. The other problem that could happen is the attackers could actually be a little bit more sneaky and try and hide the way that they're doing the attack. And let's try and look through some anti-detection or anti-forensics type of behaviors that attackers could do. So one of the very simple things that they could do is they could just rename the process, right? We can just rename it to a different name, and we can launch the service as a different service. So let's try this again, and we'll just do a very simple attack, right? So we're just going to copy PsExec. We'll just call it, I don't know, nothing, right? So we just change the name of it. Okay, and then just for the sake of this exercise, we're just going to clear the log. So we're going to, you know, clear all the evidence from the previous attack, so we can look at a new attack. And what we're going to do now is we do the same thing as we did before, but instead of, we're going to use the switch -r, which tells it to rename the service that they've created, that it creates. So the attack runs exactly the same way. Okay, so the same thing. We're going to exit out of that, and if we refresh our logs, we can look at the logs again. But I just wanted to show you in the event log first, and then I'll show you with the detection. You can see that we've renamed it, so the name is different. So obviously, if we had written a detection based on, the file names, then it wouldn't work. But the file that's created, right? The Windows, it's created. The file that's written into the Windows directory is actually going to be cwindows nothing.exe, right? So that file is not called PsExec svce anymore, right? So if we go back to recollect our thing, it doesn't matter if it's this one or that one, doesn't matter. We copy collection, just do the same thing again, and then we're going to copy our query from here, which will be our detection, right? So this is like, you know, our detection. If we do that thing again here, okay, just copy paste, but we don't get a detection. And why is that? Because the service name is not called that. Okay, it's actually called nothing.exe, the one that we're writing in the Windows directory. So this is the point, right? So basically, this is a very simple bypass, right, for the detection. If our detection rule is looking for file names are very easy to change. So it's very easy to bypass them. It doesn't mean that the detection is bad. It doesn't mean that it's a waste of time, because there's always going to be the inexperienced operators that don't do the obvious bypass, but so they will still be caught by this default behavior, but the rule is not super robust, okay, because the name of the image has been changed. Okay, so how can we make it more robust? Okay, so how do we make it more robust? So we didn't detect it, right? This is what we've done before. So what we can do is we can try and find more information. By looking for more information, then we can find things that are maybe a little bit more harder to change. Okay, so a little bit more difficult to update. So if we look at the sysmon rule, so we look at this event, in the event log, then we can see that it actually has some other information. Okay, this is the process create, right? And it also includes this information here: the description, product, company, original file name, command line, current directory, the command line. So where does that come from? Where is this original file name, product? So you can actually see, even though the binary is called nothing.exe, the description and product, they're still accurate. So what is that? So where does that come from? And I think I showed it before. Okay, so if we look at this nothing.exe, right, this is the binary, we right click, properties, and it's still signed, digital signature, and in the details tab, we can see this same information, right? So the product name and file and all this, that information is actually part of the what we call the version information. It's part of the binary. It's in the binary itself, so it's information that's embedded inside the binary. It's kind of a resource that we can read. So it doesn't depend on the file name. So when you change the name, that doesn't change, right? It's part of the binary. So sysmon adds this information, or we call it enriches the event with additional information that came from the binary itself. So sysmon is actually reading this binary and analyzing this version information and appending that to the event. So this is an example of where we can get more context by getting more information from the endpoint. Okay, so if we actually look at our detection here, so we're looking for an image name, right? But the image name is not actually enough, right? So, but what we can do is, if we made it, okay, if we look at the field, let's say product, okay, so that is one of the event data, product matches PsExec, right? Then we detect it. Then we'll be able to detect it, because even though, okay, let's just clear all. Let's just look at the row events of this one. Yeah. So even though the image itself is not matching, right? It's not correct, but the product is matching, right? So product here matches. Okay, so we can see that now it's a little bit harder. If we just did a simple rename, it's not enough, because now our detection is more robust. And that is an example of we can make our detection better by getting more context from the endpoint. Okay, so let's go back to our slides. Yep. Okay, and so we've done this. We added the detection. That's great. Okay, so how can we make it more, robust? So it turns out that attackers can, that this product is just, as I said, it's in the binary, right? So, but it's not really a critical thing. It's just a tag in the binary. So I can actually run HXD. Yep. I'm just going to open up the binary in a hex editor. Okay. And let's copy that guy. And I'm just going to search for product. Okay, but I'm going to use UTF-16 and then just search forward. Okay, so you can see that it's in there. Product name. Okay, that's not it. Keep searching. Oh, product name, sysinternal PsExec. Okay, so I can just change this. Okay, so just change 1 byte. There's actually two places in the file, so just keep searching. Product version, product name, sysinternal PsExec. Okay, so I'm just going to just change it, doesn't matter. Save it. Okay, and if I do that again, same attack. Okay, so same thing, it still works fine, not a problem. Actually, I just clear the logs because I just wanted to show the logs fresh again. Let's do that again. Okay, and then bring that back. And this time, when a process is created, you can see that there is no product field anymore, so Sysmon doesn't know how to fill it in because it's no longer there, so it's empty. So now our detection that looks for the additional information, it's not working. Okay, because where was it? Here it is. Yeah, it's not working because we've changed the product. Right, so that field is not there, and it cannot match, so it's not going to work, right? So anyway, we can just keep going down this rabbit hole of attack and defeat. But let's see, what have we learned from that? So there's a couple of problems. We just did a small exercise looking at detections, how to rewrite detections, and we found some problems with the approach. We found some we found some ideas. We got some ideas. We've got an idea of how to make this detection better, right? So the first thing that we learned is that in order to write a detection, we need an event source. We need to get that data from somewhere. We can't just write a detection out of the air. And it depends on the quality of the event source, where the events are coming from. They're telling us what's going on in the system, right? And so we can have, an event source that has a lot of information, and an event source that has very little bit of information. We can't really do a lot with it. So the quality of the event source is really critical for better detection. We need to have good event sources. We saw the process of how event sources are normally normalized to a schema, especially in a SIEM where they get put into a database. So they need to be inside of a shape. And the reason for that is that we need to be able to query them. So typically, if they go into a data lake or data mining type system, they need to be normalized and indexed. So they need to be normalized into a particular shape. And it's also so that we can compare data from different types of sources. And then the whole point of detection, we saw what detection really is. I mean, all it is just like a grep. It's a search replace. It's a search. All we're doing is we're searching through the events against a rule, which would be just a query, and that rule finds something. And if it finds something, we call that match a hit. That's all it is, right? So there's nothing really magical about it. It's just a search. And then we've seen how attackers can change their methodologies to bypass our detection rules. So our detection rules can be robust. I'm not saying that they're useless. We can have simple detection rules because not all the attackers are, going to be doing all of that. So simple rules can help, right? Still help a lot because they catch the simple attackers. But more sophisticated attackers are thinking about how our detection rules work, and they are adapting to bypass them. Right? So one way that we can improve our detection is by adding more information, more context, because that gives us more of an idea of what is really happening in there. And then finally, we saw that communicating detections is difficult because it depends on the whole system. How is the system used? If I have a friend in another organization and they have a different system, how do I explain to them how to detect? And I mean, of course, I can explain in words and people will understand, but we really need a machine way of being able to, automatically send them a file that they can use. And this comes down to an automation, right? We need to be able to manipulate a lot of detections quickly. So the tech stack is really important. All right, so these are some lessons from this part, and let's in the next part we will learn about how to improve this situation. Okay. In the last section, we discussed how to write detections for this particular attack, and we saw that there was a problem in sharing that detection with other with people who had different systems, different detection platforms, different detection stack. So in order to solve this problem, we have something called a Sigma standard, Sigma rules, and Sigma rules are supposed to make it easy for us to share the detection or this idea of what to detect with other systems, and trying to kind of make it possible to convey this in a more machine readable way. As I mentioned before, you can always just discuss what the detection is going to be. Like in this case, what we wanted to do is look for a certain name of an executable launching from the Windows directory, right? But how to actually implement that inside a detection system in an automated way, that means that we need to actually create some kind of machine readable format or standard that we can use to just convey this idea. And that's what Sigma is for. It's for being able to write these rules which convey sort of like the vibe, I call it, of the detection. So they're not really directly usable in a system, in any particular system, but they just convey this kind of idea of what exactly to detect in a machine readable way. And that's kind of what we are going to look through in this section. All right, so the idea of a Sigma rule, this is what a Sigma rule looks like. You can see here, and then we have these different parts to it, and it's written in YAML, which is a type of formatting, with where we indent subfields and that kind of thing. So the indentation is important in YAML files. And you can see that we have a couple of fields. There's actually a lot more different types of fields that you can have, but we won't really cover them too much. These are sort of the essential fields that are the full rule is in this link here if you want to look at it. So let's have a look. So again, the Sigma is supposed to be kind of like a grep pattern or a Yara signature or some kind of match that will match an event log, right? And it doesn't. The important thing about Sigma is it doesn't specify anything, right? There's no hard specification of what these fields actually mean. It's quite wishy-washy. It's very vibey. You're just kind of conveying the sort of a vibe of a detection. It's not really very specific, and it's trying to do that in order to try and be more portable, but it ends up being a little bit difficult to work with when you don't know exactly what is going on, right? So let's have a look at some of the fields that are shown in the Sigma rule. So we have a log source section, And as you can see in this example, the log source, it has a category and a product, but it doesn't really tell you anything about which log file that's coming from or where it's coming from. It just says kind of like, oh, it's just process creation. Just, that's the vibe of it. We're just getting some process creation events. Awesome. And then we have a detection clause, which contains selections and then a condition that combines them. So in this example, we have a detection clause here, then we have a selection, and we're saying the command line has to match, or it has to be this, PsExec. Okay, great. That doesn't really, say what is the command line, whether the command line is going to be in a particular field or in the event anywhere. It doesn't really say that. It's just a vibe. We just kind of like get this vibe of a command line. We're going to look for a command line that is, in this, that contains, this PsExec SVC. And then the condition, which is a logical combination of all of these selections, right? So the important thing here is that it's all very abstract and it doesn't really map to an actual field in the event. As we've seen before, the events may look different because the data structure is different. And so to kind of help to fix that, we don't define what log sources are actually available. I mean, are we actually even collecting process execution event, process creation events? We don't know. It really depends on the stack, whether we've configured it. As you can see, we've discussed before that if you're collecting 4688, you have to set a policy to get the command line. So that command line field doesn't even appear if you don't set the policy, and that's your detection stack, right? So it doesn't tell us anything about whether the field or the event log are actually even available. It doesn't tell us anything about how the event is structured. It doesn't say what fields are available and what they're called or what the name is. It's very, very abstract. But so really the intention is just like a vibe. Just convert the vibe of the detection. And in practice, what we do is we use something called a Sigma compiler for a particular platform, particular stack, to convert this vibe into something real, right? And let's have a look at the Sigma rule syntax, right? So I've just gone through. If you look through the documentation site, then it tells you all about the Sigma rule syntax. It's pretty simple. It's as I mentioned, it's in YAML. The selections, you can have multiple selections, and then you can combine them with conditions and so on. You can look at that link for more information about the particular format, but that's basically all enough to get started. It's pretty simple format. The other interesting thing is that there is a thing called a modifier, and a modifier is something that applies to the field to modify it. So it sounds like when you read the specification that you can put any kind of modifier together, but that's not actually the case. It just doesn't make sense in a lot of cases to just cascade them in an arbitrary way. Certain combinations make sense, other combinations don't really make sense. But you can do things like the target file name ends with command line, right? So that is a matcher on the command line, basically. And we've got a regular expression, we've got a contains. These are probably the most useful ones. And in Velociraptor, we have a VQL modifier, which is an extension to Sigma where we can run VQL functions and make more complex matches. Okay, so how are you supposed to use this? And so what actually happens here is that we can see that this is our detection stack that we talked about before. And remember how we said that our detection rules are different because different backends have different schemas and different ways of querying them. But then we have our Sigma rule, and that Sigma rule is used to generate different detections. So the Sigma compiler is used to convert the rule into the platform-specific detection. And how does it actually do that? How do we, use the Sigma compiler to resolve that ambiguity that we talked about, the rules being very ambiguity and just the vibe, right? How do we turn that vibe into something real? So we have two things. We have the field mappings, and the field mapping is just a way of mapping between fields in the Sigma rule, which were abstract and didn't really correspond to any particular event. Mapping that to an event, to an actual event field that is collected in that system. And then we have the log sources, which define what events are actually available on this system, right? So that log sources defines for us what kind of events are available. Are we collecting process execution at all? So it maps between when the rule says I need process creation, then the log source tells us where we're going to get these events from, right, on this system. And then finally it's a compiler, so the Sigma compiler converts it to some kind of query language that is used by the backend. That is for the proper, so for example, if you're using Elastic, we've already encountered the ECS, Elastic Common Schema, then the Sigma compiler would map the fields in the Sigma rule to a field in the ECS schema, and then generate Elastic queries against the backend to detect those rules, right? So that's what the Sigma compiler is for. Now in Velociraptor we don't actually have a compiler, right? So we use Sigma directly, and so generally when you have, so we call it in Velociraptor, we call it a model. A model is just a combination of field mapping and log sources. We don't really compile anything in Velociraptor, so we don't use a compiler as such. We just directly feed the field mapping and log sources to the Sigma plugin. But it doesn't matter, it's kind of the same thing. But in our terminology we use the word model to kind of convey this self-contained, self-referential model that we can use to write Sigma rules. So generally you can't really read a Sigma rule without knowing the model that's used to interpret it, knowing the specific compiler that's going to be used, because that determines the type of fields that are available and the type of log sources that are available, because nothing is actually specified in the Sigma standard, right? It's not specifying anything. So we actually just use the Sigma compiler model as the way of specifying a particular flavor of Sigma rules. It's a very wishy-washy, vibey type, just conveying the vibe. And that's why it's not really portable between systems. Only the vibe itself is portable, but the model, the standard is not really portable. If you just take a random Sigma rule that's written for a particular platform, you can't just expect to run it on another platform without carefully making sure that the two models are compatible, that the models that we are, where it was written are the same or similar to the model that, is intended for. So for example, like if you're going to use Sigma rules that are written for Elastic Stack and you're just going to feed them into Velociraptor, you better make sure that the Velociraptor model is more or less compatible with the ECS Stack model so that we can consume those rules properly. So in Velociraptor we don't actually have any compiler, we don't compile anything. We just have a Sigma engine that's built in, and we're actually starting to use Sigma for anything that requires detection. So we use it everywhere, and we will use it more in the future. So it's a pretty significant part of Velociraptor now. And the model, we have this concept of a model again. It has a model definition which defines log sources and field mappings, and those are the ones that create the interpretation that we need of the rules. So in the Velociraptor terminology, the Sigma model, when you hear us talking about Sigma model, that's similar to a Sigma compiler that people talk about for SIEM systems, right? Because we don't really compile anything, we don't call it a compiler, so we call it a model. But it's the same kind of idea. It's basically the environment in which the rule must be interpreted and understood. In Velociraptor, the models and the rules are pushed to the endpoint because we evaluate directly on the endpoint instead of forwarding the events first. So let's have a look at this is in a diagram form. So with Velociraptor, we have the endpoint here, okay? And what we do is we push the rules to the endpoint and the model as well. And then we're running detections directly on the endpoint, right? So if we have different log sources, and it could be event logs, and as you'll see, it could be many other types of event sources, we basically filter them through these rules, right? So, and then just forward the matches to the server and possibly a SIEM, right? So, so if we might have 1 million log events, right, coming in here, and then we might only detect 50 detections and then forward them. So you can see that already we're reducing our data use. We are only forwarding those logs that are significant and mean something and actually match the Sigma rules that we are looking for. And that allows us to be very selective and also move a lot less data across the internet. Whereas, in a SIEM system, you would forward all these logs through the internet to a backend system and then query it there. We'll talk about that a bit later, but that requires moving a lot of logs. We'll talk about that a bit later, but that's the model here for Velociraptor's Sigma architecture. So we need to maintain our sort of official curated Sigma models. So we have this project here. It's another project, separate open source project to maintain Sigma models for Velociraptor for different situations, and also curate different Sigma rules. So the main goal is to separate the maintenance of the model and writing the rules. We want to make writing rules really easy, so that you don't have to think about it. And maintaining the model is a little bit more complicated. It requires understanding the architecture pretty well. So we try and outsource that and allow people to write rules. So we have this here. This is the Sigma repository, and we can have a look at it in a minute. But let's there we go. Okay, and we will go into that in just a minute. Okay, so let's go back to the slides. Where was it? Yeah. Okay, so okay. So this is the site. Let me open that in a new tab. And we can see that over here we have the different models that Velociraptor uses. And you can see different, we'll just see what each model looks like. In this case, we can look at, these are the different models that are available, and we can also add more models in the future, but designing a new model is a lot more involved, so it's best to use the same one that are available and maybe just extend them. We'll talk specifically about them later. The first model that we'll talk about will be the Windows base model. And this model is written specifically so that we can consume a lot of public information, public Sigma rules that are available, in the public. And because most of those public rules are actually written for SIEM systems like the ECS schema, or elastic type schema, or Splunk, these kind of things. And so this is a model that's reasonably compatible with the Sigma rules that are in the wild, and it will work with most of the Sigma rules out there. And because those rules are written to work with Windows event logs, then this model also works with Windows event logs. And the most extensive rule set that we have is the Hayabusa rule set that uses it. So let's have a look at how we understand this model. So over here, this is the documentation page for the Sigma base model, and this is all the different log sources that are available. Okay, and we can search it. So for example, sysmon. So sysmon is the one that we would have used before, is probably the most commonly used one. And we can open the details about it. And you can see that when your rule specifies the sysmon log source, you would write it like this in your log. It would be product, Windows, service, sysmon. And that's if you write your rule that uses that, then this will be the log source that we use. And you can see that it has VQL to basically consume the events from the Windows sysmon operational log. So it just consumes events. It's pretty straightforward. Okay, so this just shows you how to navigate the website a little bit. And this log source, this is the query, and this is what we would use in the rule to specify this log source, right? Okay, there we go. Okay, and then we have field mappings. So the field mappings, let's go back. This section, field mappings, shows us all the different fields mapping. So in Velociraptor, the field mapping just maps via a VQL function. And so for example, like if we look at command line, so when in the rule when we say command line, then it's going to run this VQL function, right? So it's going to try and pull that out of the event data, or just the command line. So this basically is just a way of how we resolve the fields. So you don't have to in the rules, because Velociraptor's Sigma implementation can also use dots, so we can access that field directly. But these are the fields that if you take a rule from an external source and it refers to command line, then you can check to see, are we going to be able to understand that at all? Yes, we will. But if they look for, like, I think some of the rules are like using like grandparents command line, that actually doesn't necessarily exist, right? So we may not have a mapping for it. Okay, so this is how we just navigate the the documentation page. So let's see how we would use that. Go back to our Velociraptor here. Okay. And let's just put that guy over there. Yeah. And now this guy can go to full screen. Yeah. So how do we get these artifacts, these curated artifacts? So if we are in Velociraptor, we can just automatically import them, or we can do it manually. There's two ways. So it depends on whether you have the server can go out and download those artifacts directly. If you have egress or something like that, egress filtering, then you can't do that. If we have, these are the different artifacts that we have with the curated rules, and it explains to you here how we can do it. We can either download them automatically, or we can just download them via zip file. I'm just going to show you how to download them via zip file, because that's going to be the easiest way. You just download the zip file, there it is, and if we open the zip file, then we can see there's all these YAML files in here. These are the artifacts, different types of artifacts. We can import them into Velociraptor. So where we do that is we go over here, view artifacts. This shows us all the different artifacts that exist on this system, and most of these are built in. They come with Velociraptor, so we can collect all kinds of things. But what we're going to do is look for those artifact packs. So we're going to upload an artifact pack, click this button, and then choose that file from the downloads directory. So this is the one, Velociraptor Sigma artifacts, right? And we're going to open that and then click to upload. And so that actually shows us these are the different artifacts inside of that zip file. We can filter of them, but we can just import all of them. So let's just import all of them, and that will import all of these artifacts, and you'll see them appear in the UI with a little customized icon next to them. That means user customized, right? So they are customized ones, and the ones without, they are built in. So okay, so these are the different ones, right? And so we can actually search them, Sigma, and that shows us like most of the ones that we've just imported. And we have, this one is the one that is using the base artifact and importing the Hayabusa rule sets, right? So they're all in here. So let's go through and see how we would use something like that. Okay, so we have just gone through, we imported the artifacts, and we've learned about the Sigma rules. Let's do a recap. So this is we're going to go do that in the next part. So at the end of this section, what have we learned about Sigma? Sigma is a vibe, right? It's only about the vibe. It's basically not really well defined. It's not well specified. It's just telling us about roughly how we would detect something. So there's actually a gap between what is required from just having a Sigma rule to being able to actually run it on the system, and that is filled by the Sigma model. So you can't really just blindly copy a Sigma rule from one system to another, because without understanding like intimately what kind of events are available, what fields are available, what field mappings exist, and so on, it's actually not a really very portable system. You can't go from Elastic Sensor to Splunk without having a proper idea of how comparable these two systems are. But those systems that are very commonly used, Splunk, Elastic, they're used a lot, and so there appears to be almost like a standard flavor of fields that they work fairly well, but for other systems they may not work well. For example, if a Sigma rule is written for EID1, which is sysmon, which always, for example, gives fields like command line, it gives fields like the product, like original file names, which we've seen before. And if you're taking it to a system that doesn't have sysmon, but they use Windows audit log with EID 4688, it's not going to work. Or it might work. It may or may not work. It probably won't work, right? Because 4688 is missing a lot of fields that sysmon adds. And so the rules may just blindly refer to a field like the product string that we've talked about, that is not in 4688, right? So they'll never be able to match. So the risk here is that we can convert those rules blindly, and then we'll never be able to, they just will never ever fire. And we wouldn't know because we had no idea. And that risk is actually pretty real. It's a false negative risk. We're going to write all these rules to detect these attacks that will never work. And we don't know that. This is where the engineering part of detection engineering comes in. We have to write tests and all that sort of thing to make sure that these rules are actually going to work in a different environment. So there's some traps. All right, so let's focus more on the Windows event logs for the next part. And this is really about this kind of like standard, bread and butter Sigma applications. Most Sigma rules are written for event logs, to look at event logs, because they are normally relying on being running in a SIEM system, like an ECS system, Elastic SIEM or Splunk or whatever. And so those are normally event forwarding systems. So they are really looking at event logs. This is the Windows event log. And a lot of people don't know that you can just right click on the event log and just disable it. So you can just disable the logs. You have to be admin and so on, but you can turn them off. And then, if you're just relying on event logs for your detection, it's not great. It's good, it's okay, but it's not super great because it's very easy to bypass these detections. So, and then, event logs are stored in files on the system, so we can always delete the files or whatever. So we actually, so it's pretty easy to manipulate. Okay, so this is what your average typical Sigma rule use case is, right? You have your event logs, and remember before when I talked about the Velociraptor Sigma model, we actually did the sigma matching on the endpoint and only forwarded some of the events, or the ones that matched. But the way that sigma is used, usually is we have these event collectors, event source forwarders. It could be Elastic, could be Microsoft Event Forwarding, whatever. And then we forward all these events over the internet to a SIEM, a data lake solution, so Elastic or Splunk or whatever. And then we have some SIEM query language that we use to query that. So obviously the problem is that we're going to forward tons of event logs over the internet to this massive storage thing, and then do the query here. So all of these events that are coming through, 90% of them are not relevant, right? Because they're not going to match any of these queries. But we have to forward them before we can query them. So this creates some problems. The pros of using event logs is that they're part of the system, right? So it's easy to get to them, and we have lots of solutions for forwarding the events. We have vendor-specific ones like Elastic ones, Elastic Client, or we have built-in ones like Microsoft Windows Event Forwarder. But the problem is that now we have to choose which events to forward. We can't really absolutely forward all events because it's just too many, and at scale that becomes prohibitively expensive and also just a lot of network traffic. And so we have to choose. Like, we're going to say, okay, we're going to forward sysmon events because they're super valuable, but maybe we're not going to forward Windows bits client operational logs, or terminal services. These terminal services are really valuable. We'll probably forward those, but we're not going to forward like audit events. So we got to do a trade-off. Which ones are we going to forward? Which ones are we not going to forward? Some of the events are really noisy and low value. Some of them are high value, so we might forward them. That kind of thing. And then the other thing is that detection is happening on the network, right? So the events actually have to make it to the SIEM, or we're not going to detect it. So if this machine is offline, we're not going to detect it. We can't find anything, and so we can't really do the response until we get there, until we actually get to be online, right? So this is also a problem. And then we also have a long lead time. By the time the events are all forwarded to the SIEM, and then we query them, and then we detect something, and then we have to go back to the event, to the original one, that increases that loop. We might want to get more data. We'll talk about that a bit later as well. So this is kind of the disadvantages with this kind of scheme. But let's go back to look at the event logs. And as I said, in Velociraptor, we use the event logs. We detect on the event logs locally. So we do things a little bit different. But we're just going to go back and show you how Sigma can be used to detect event logs. Okay, so what we're going to do is we're going to use a notebook. And the notebook is sort of an interactive, which we've seen before. We're going to create a notebook. So click on that notebook side here, and the big plus. And what we're going to do is call it something. So let's go with it like Sigma plays. We're going to play with Sigma. And for the template, we're just going to use the default template for now, and then launch. Right? So that creates a new notebook, and we're basically going to see like a little welcome message here. So this, you've got to click on this, by the way, because otherwise like people don't know. Click on it, and then you'll be able to edit the cells. So this is composed of cells, and then each of them can be edited. Then we're going to add a new cell and add a VQL query, right? So here we can actually run VQL, and we have command line completion, select star from info is like our hello world. It's telling us things about the server, that kind of thing. So these queries are running on the server, right? But in this case, because we are running it locally on the system, then we can actually do Sigma stuff on the server as well, but it's just running on the same system. So it gives us a really good way of interactively playing with VQL artifacts. All right, so let's see. So click on that to edit, and then click on that to get a new cell, and then we can start to write some Sigma events, right? So I don't really want you to edit it to copy it from this, so that's why you can just copy it from here. So we're just going to copy this, right, and then go back to our, okay. All right, so what we see here, we see a little bit of VQL query. We define the rules, which are a sigma rule. So this is just a sigma rule in a string. This 3 dots, just 3 quotes, just mean long multi-line string. So we can split it across lines and so on. And then so we can see a couple of components that we talked about. So this is the title of the PsExec service, right? And then this is the log source. Remember that we went in here. We're going to use the Windows base event, and it's going to be the sysmon, right? So we're going to look at sysmon, and so we just copy this, where it says log source. That's what we're going to use, right, for our new, and that tells Velociraptor to use that one, that log source. Okay, and then we have a detection. The detection clause. Now these selectors can be like anything because they're just words, so it doesn't matter. But we're going to call one of the selectors is event ID, and we're going to use a field called event ID, right? And again, if we look at our field mapping, event ID, then we can see that event ID in Sigma is mapped to system event ID value. Because remember that was the rule that the field that we used before in our query, right? When we did our freeform query. All right, and then the selection 2 is going to be the image field is going to match this regular expression PsExec.exe. Okay, so image is event data image, right? So this is the same thing. So now we're seeing that how this Sigma rule is mapping back to the VQL that we used before. And then we're going to call this Windows Sigma base. Now the base artifact is the one that simply defines the model and the field mappings that we saw before that are described here. And so we don't really need to worry about that. We don't care about the specifics of the model. We just say we want to use this model and these are the rules that we want to run. So let's do it. And then immediately we see a match, right? So boom, we've got the detection. And we see this is the log, the query log. So it's telling us a little bit of information about like how the query is running and what's it doing. And so we can see immediately, okay, it's loaded one rule into one log source. We have 284 field mappings, and then it consumed 135 messages from this log source. And against that one rule, it took a few milliseconds, and then it found one hit. So it's telling us a bit about how this is going. And if we look at this row JSON, that shows us so this is the table format, but we're just going to be get used to looking at the row data. So the row JSON here shows us the row data, and you see there is actually a field called underscore event, and underscore fields are normally hidden, so we don't want to show them in a table because it's a big complicated field. It's not super relevant, but it can be relevant. But we're going to look at it in more details now, because just to understand what is happening. But that is the actual original event that matched the rule. So whenever a rule matches in the Sigma, then it's also reporting to us the actual event that matched, so we can see why was the rule false positive or whatever. Like this is all the information we know about it. So it's got all the data, like the product, company. This is everything that sysmon added to the event is in here. And this, we are actually only just matched on this image, right? And also here you can see we got system event ID value 1. So we matched on that as well, because that was our other condition. But we can see all the data comes, and so that gives us enough context to say, well, was this, false positive or not, whatever, right? So we can see some information there. You can also just hide. So this, because it's an underscore, it's hidden. You can enable it, but then it gets quite squished at the end. So we can. Oops. yeah, we can just add the event here, right? We can, you know, open it up and take a look. This is the system part, this is the event data, you know, that kind of thing. Okay, so so that shows us how to write a very simple Sigma rule. That's actually pretty straightforward. And that's what Sigma is, right? So we've just written our first Sigma rule. Yay. Okay, so this is how we test it. We write it, we click, you know, save to calculate it, and we see the rule being detected. Okay, so what advantage is there for pushing the Sigma rules to the endpoint and analyzing them directly on the event logs that are existing? So this is used mostly in Velociraptor, in many other DFIR tools now, as a way of getting quick, rapid triage going. Normally, when you're doing forensic response or incident response, you come up to a machine and you have no idea what happened to it. And so this triage gives us a good way of finding out, you know, the first thread that we're going to pull to untangle this question of what happened. And doing this with quick running Sigma rules on all the event logs is a quick way to do that, because a lot of the time those machines, they don't have EDR, they didn't forward the event logs in the first place, and so we don't really have detections anyway. So we can use these detections to essentially grab the logs to find the important things from really quickly. And it's okay to have noisy rules, right? Because we really, in a use case of triage, we don't know what happened. We want to get noisy rules, so we want to see like whatever happens in there. It can take a long time though, because we can actually look at lots of logs and maybe evaluate thousands of rules, right? But in the end, we're going to get a quick picture of what what's available, what happened. So we often use this Windows Hayabusa rules artifact, and Hayabusa is a project that that curates the original Sigma HQ rules and also has other rules. So we just kind of use their rules as well and integrate it into our Sigma model. And you can see that there's about 4,500 rules now, and so a lot of them are really noisy and low quality, but that's okay for triage, right? That's an okay trade-off. Now, if you go to our Velociraptor Sigma rule site, then you can see here we have our Windows Hayabusa rules artifact, and you can search a bunch of rules here. So for example, like if we want to know PsExec, there's a whole bunch of rules that are looking at PsExec. For example, this one, PsExec service child process execution. If you click on that, you can see the rule, and this is a process creation, and again, and it's looking for EID1, and it's looking for when the PsExec SVC image user is running as authority, or that's when we're running a system, right? So that's kind of what we're doing now, and so it's looking when this process is running a system, right? That's what that rule is looking for. So there's a whole bunch of PsExec related rules that we can use, right? This one is using the system event log, so it's a different event log and so on. So okay, so let's see how we would use something like this in an incident response triage type scenario. So let's go back to our endpoint here, and we're going to collect this artifact. Okay, so we're going to go a new collection, and let's look for the Hayabusa rules artifact. So there it is. And all we have to do when we're doing triaging, we want to be really quick. We don't want to think too much. We just want to just go, right? So we have this artifact. We can edit some of the parameters, and just for this exercise, just because I don't want it to take too long, let's change the rules to what did I say here? Critical and high and stable and test, right? So stable and test, right? So just not all the rules, because there's just a lot of really noisy rules, and you can see we also have by default a bunch of exclusions, and these are all very, very, very noisy rules that we don't really like to run, and they just take a long time to evaluate. They don't give us much. So just for this exercise, we're going to restrict the rule level to make it a little less noisy. And then, you can also time box it or whatever, but this is usually not needed. We'll just click launch and we'll go. And what that will do is it will now push the rule set to the endpoint. It's not very big, and then start collecting all the logs. Now we can see those query logs here coming from the endpoint, right? And we can see immediately it loaded 2,000 rules, okay? And we're going to read 22 logs, or 22 different event logs, and apply these rules to the event logs. And as you can see, there's kind of unusual event logs like WMI and ABEX deployment, code integrity. So normally you wouldn't be forwarding these events to your SIEMs anyway, right? So even if you had a SIEM, these will probably not usually be forwarded, so you wouldn't really be able to use these rules in a event log forwarding type system, right? So some of the rules are looking for files that aren't there, so it's just telling us all that stuff. And then we can see more logs, and as we're consuming these kind of so many messages from the different log sources and applying them to the different rules. This is a security log, so it's kind of large, and so on. So basically, because it doesn't take long, see, a bit over a minute. We just went through and we just applied 2,000 detections on our logs. It's very quick, and let's have a look at the type of detections that we have. So let me just see the slides where are we up to. So we did this, we started to collect it, and we noted how those events are collected and how Sigma works in Velociraptor, right? It loaded the rules, it applied them to the log sources, and it started to consume logs, event logs from these log sources. Okay, and then now we're going to look at the results. So it came back with a bunch of results. As you can see, there's 300 hits, and normally there would be like thousands of hits because we might have noisy rules, but because we cut down the rules to save time here, so it's not too many. So what we're going to do is we have a whole bunch of these. So normally we'll have too many to review manually, and even at 300 it's boring, right, to look at this. We don't want that. What we actually care about is we want to know what type of things are going on the system. So we don't really care about the specific things. So some things will be like false positives because this is how the system is used, but some things will be unusual. So when we're looking at the type of things that are happening, then that gives us an idea of what kind of activity is normal and what kind of activity is not normal. And so you can see there's a whole bunch of different events that are firing, right? Different rules that are firing. So if we hit sort here, that's going to sort this table by the title of the rule, right? So we have a whole bunch of rules, and then as you can see, these rules are, because we sorted them, the rules that are all the same will be like next to each other, because that's what sorting does. So now we're going to do a technique called stacking. Stacking is when we look at all the events of a similar of the same type together, right? So we basically, so you see how we've got this Windows Defender threat detected, like this rule that's fired, there's lots of the instances of the same rule being fired, right? So I don't care about each instance, I just want to know what rules fired and how many times they fired. So this is stacking. So when I click this, so every time in Velociraptor when we sort, we also do the stacking automatically. And so now we're going to click stack, okay? And that shows us the stacking table, right? And what it shows us here is the number of unique rules that are fired and how many times they fired, right? So for example, like we see this suspicious service path fired 130 times, right? So there's a lot of them, but it could be a false positive. Maybe the rule is just too loose. It doesn't really show us very much. So we could look at that. All right. So we want to know now. So we know that fired 130 times. So now we want to see. Okay, let's have a look at those guys. So we click this link here, and then we can see all the instances of that suspicious service path, and that particular rule is looking for, like, if we don't know, let's look for what is this rule, suspicious service path. Yeah. So that rule is looking for when the service is installed. What do we got? So this is where, you know, the service is installed on a suspicious path or spawns a what is that? So it's a system event log, suspicious, the image matches this regular expression, and yeah, so we basically, it just looks for a service that is unusual. So okay, so that's this. We've got a whole bunch of, you know, interesting things going on here. Let's go back to the stacking, and we can see, okay, there's some PS lateral movements. Okay, so there's all those PsExec rules that are firing. Okay, and then there's outbound RDP of a non-standard tools. Let's have a look at that. All right, so we can see that there's some, you know, RDP stuff going on, and so on. So you can see there's, you know, there's some threat detected, defender detected some threats. Yep, so we've got some Trojans, that kind of thing, whatever. So we can see that there's actually, so doing it this way allows us to quickly triage the endpoint. We can immediately see what looks suspicious here, and then quickly decide whether these are false positives or not. Yeah, for example, this one cleared the logs. Why did it clear the logs? Okay, so this is because we cleared the logs. So, you know, so we can see whether so that's the triage. So you would quickly look at them and say, yep, something weird is going on this machine. A lot of the time, these will be false positives, but then we can, you know, confirm that quickly. Okay, so you can see that doing it this way really saves a lot of time, because we're reviewing the logs really quickly and just immediately just pulling out the most suspicious things automatically by the Sigma rules. And so the Sigma rules are actually creating this kind of triage package that helps us to identify what's going on. It's okay to have noisy rules in this case, because we can just immediately say, oh yeah, those rules are noisy, let's ignore them, or just look at a couple of instances and say, on this system this is okay. They don't really have to be tuned to the system, right? Because we can say, on this system PsExec is used heavily, it's probably normal, we won't worry about that in the moment. Again, we just want to get the vibe here, right? So it's just a quick vibe check. Then we can drill down later and get more details if we need to, but this is a triage. And if we do that as a hunt, that means we can run it on all the endpoints in the environment really quickly and get and quickly triage the entire environment this way. So using these, I just wanted to have one slide here to look at triaging with on-endpoint Sigma evaluation, like we've done with Hayabusa now, in Velociraptor, and many other DFIR tools now as well use that technique, versus SIEM with log forwarding, which is your normal, you know, SIEM type deployment. When you forward things with a SIEM, you've got to figure out which ones to forward. So we're not going to see all the events. We're going to see some of the events. So we already have a disadvantage. We're not going to be able to match rules on unusual events or very noisy events, because we're going to need to increase our storage cost. Every time we make a decision of forwarding one event log over another, then it involves cost and bandwidth, and then of course because we have to be online. So these are a problem with the SIEM system. But when we do on-endpoint evaluation, we don't care about the noisy event logs. It just takes a little bit longer. That's not a big deal. And we can do it at scale. We can run a hunt across the entire environment and quickly filter all of the event logs that are on the endpoint really fast without having to worry about forwarding all that data into a big data storage data lake type thing. So we can do it at scale very cheaply with a very efficient network transfers, because only the ones that match are transferred. But if someone deletes the log files on the endpoint, well, then we're lost, right? Because we don't have anything to work from. So that's the disadvantage of this technique. Ideally, you want to have both, but you know, sometimes in triage you don't have both. We're going to look at customizing Velociraptor artifacts in the next section. So we'll just do a little bit of a break and we'll come back. Okay, so in the last section we saw how we can use the curated rules to quickly triage an endpoint, but usually those rules will be quite noisy, and you might want to customize those rules for your own purposes, right? So it's actually quite simple to do, and I'm going to show you now how we can customize our own Sigma rules with the Velociraptor Sigma curated set. All right, so we might want to modify the rules because to suit our environment. So what we will do is, first of all, we go to our to the Sigma website, and then we're going to download the specific artifact pack for this artifact. Okay, so because the Sigma artifacts are only, okay, so here's the Hayabusa rules, and over here we have the Hayabusa rules.zip file. Here's the full webpage to explain how to customize it, but I'm just going to go through it real quick. So this one downloads the zip file that contains all the parts that make up this curated artifact. Remember, there's 4,000 rules, right? It's quite large. And if we open it, it's a zip file, and we can see a number of things in here. We have the original rules. These are the original Sigma rules that are used to build this pack from. But as I mentioned before, a lot of these rules contain a lot of, you can see it here. So there's a lot of unnecessary fields like description, references, dates. They're useful, but we basically don't want to be sending all that or packing all that additional information in the artifact, because we want it to be small and fast and efficient. So we generally take these original rules and we strip a lot of the fields out to create smaller rules. And so these are the two directories here that are packed in the zip file. Here we have the original rules, which have all the fields, and then the stripped down rules, which just has the stripped down one. And then we have the actual artifact here, right? That's the artifact. And then we have a little Python script here that we can use to build up this to build this up. So let me just extract this. Okay, extract all. Yep. So we'll just extract it. There's going to be a lot of files. It will take a couple of seconds to extract it, but then we're going to use that to repack this artifact, change some of the rules, and repackage them in a new artifact. So just like before when we did it here, we collected this artifact. We can repack it with our own additional rules. We can change the rules, customize it, whatever. Okay, so that's okay. Now that we've extracted the files, then we can see the files in here, right? So what we're going to do now is we're going to create a new directory. So for this example, what I'm going to do is just show you how to pack one rule, but we can do many different rules, and we can change the existing rules, but just to show you this one rule. So we're going to create a new rule that we did before, right? We're going to make it a new text document, whatever, and we're going to call it PsExec.yaml, for example. Okay, and we're going to paste the detection that we had before. So in the notebook we had it here. So this rule that we've developed, we're just going to copy that into Notepad and just save it. Okay, so we end up with basically this is a new directory. We created a new directory with our original rule, with a new rule that we created, and we could just repack that. So let's go back to, okay. So if we look at that directory that we were in, so we have the new rules are in here, But we can also edit the existing rules, it doesn't matter. And then we have a compiler.py script, right? So let's just look at the help for that, -h. It's just a quick Python script, really simple, that just repacks that the new artifact. Okay, so we're going to use the help, right? We're going to create a zip file, my pack.zip. Okay, so it's going to be my artifact pack. We're going to change the name of the artifact. We're going to call it my Sigma artifact. Okay, and the artifact that we're going to repack would be the original Hayabusa rules one. Okay, there. And we're going to use this directory, rule directory. It's going to be this new directory, which only has one thing in it for now because I just want to show you one thing. So we're going to go ahead and do that. And what it will do is it will repack this artifact into this pack. All right, so it creates a new pack. Let me quickly show you what that looks like. So we're going to have this zip file and it just has this artifact in it. And all it is, we've created this artifact. It's just a YAML file. It's the same as the Hayabusa one, but the actual content of the rules has changed. So the rules themselves are changed. But as you can see, all it is it's just calling the base artifact and just passing the rules to it. So this is just, it just contains the rules. That's all it is. So let's import that again. Okay, and we're going to get that file, my pack, yeah, and upload it, and it's going to have this artifact, right? So this is the new one we created, so let's import that. So, okay, so now we're going to collect our new artifact, my Sigma artifact, right? And yep, and then we just launch it. So this new artifact just simply has the custom rule in it, and you can see that we have one rule. There's only one rule, and you know it works on sysmon. So yeah, that's the rule that we're going to be using, and then again we detected it. So that is how we would package our custom artifacts into the artifact pack. And ideally, you'd have your own artifact pack that you would manage for your own purposes. So we've just gone through the process of how to do that, changing the name and compiling it and creating a new artifact. Really all it is just a compressed version of the rules, and we're just passing that onto the base artifact there. And then we collect it. So the same thing. All right, so that was kind of cool. We could use the Sigma rules to look at the event logs currently on the system. But what about but that just shows us historical events, what happened in the past. But what we want to do is we want to actually do real-time detection. As soon as something happens on the endpoint, we want to get told, hey, something happened on the endpoint. Can we use Sigma for that? Of course, that's kind of what Sigma is for, right? Detection rules, but can we use them for real-time detection? Well, Velociraptor has a way of running real-time detections on the endpoints, and this is called event queries. Event queries are a special kind of VQL query that runs, in real time, and we can do that by pushing the event queries to the endpoint, and then it just runs on it. And every time that there is a Sigma hit, that is passed back to the server. So the hits are passed back in real time. And that's how we can do live detection through Sigma. It's really cool because we get hits immediately, and so if the log files are deleted off after a while, well, we've already done the detection, so it doesn't matter. We can capture the critical information of the system. So when we're doing live event detection, then we can capture critical information of the system at that point. What users are currently logged in, where are they coming from, what TCP sockets are open, all of this ephemeral data, that might disappear by the time the SIEM is reporting the alert, and then people in the SOC go back and have a look. Those ephemeral data might disappear. So if we're doing this detection in real time, we can capture all of this immediately. All right, so how do we do that? Well, we're still going to work with the Windows event logs for now, but we know that the event logs are files on the disk, right? So we can, and so far we just read the file and parsed all the events out of it and just ran them through the Sigma engine. But what we can actually do is watch the file, to watch how it changes. And this is a screenshot from the debug console of Velociraptor. And just to show you what actually we can do with the event logs, is we can actually just follow the event log or look at them, check them periodically for new events, and then only process those new events as they occur, right? So in this case, this system was up for a couple of days, and we looking at the log every minute, okay, and checking to see whether when was the last event log. That doesn't take long at all. And then we parse all the events since the last minute, so it's only 1 minute's worth of events that we are pulling out, and then we are applying those scans. Actually very cheap to do, very low overhead, and so it's actually quite efficient, much more efficient than other methods that we'll talk about later in terms of CPU use. So let's install that thing. We're going to install the Windows Hayabusa monitoring artifact. So it's the same artifact, but it's the live detection version of that artifact. So let's go back to our Velociraptor, and we're going to go to the client events screen, and we're going to install an event monitoring for this client. So we're going to update the client's monitoring table here. Click on that, and monitoring table are applied by labels. So just for now, we're just going to apply it to the all group. So all clients will get this new these event artifacts, and you can see that this one is a default one that happens all the time, but we're going to add a new one to this group. So we're going to select artifacts, and we're going to search for Hayabusa. Okay, so this one, we're going to, again, let's change it from critical and high, critical and high, and stable and test, right? So just to make it a little bit less noisy. And here it's actually more important to make sure that there's not too many false positives, too many noisy ones, because they are always going, all the matching ones will be forwarded in real time. And so if we end up forwarding thousands and thousands of events, I mean, that's a lot less efficient. And so this is more important to make sure that they are, well tuned. And this is the VTX frequency, which is how often we scan the logs. And just for now, we're going to make it like really fast, because we just want to see the results really quickly. And it will just look at the logs every 2 seconds to see for new events, so it will be much faster. So we'll just launch that. And what I will do is it will push out, we just can do that again. And we can, select the artifact here, Hayabusa monitoring, and what we are seeing here is the Velociraptor timeline viewer. And over here we can look at the different types of things. If we just look at the logs, okay, then we can see how the Sigma rules are installed, which is similar to how it was before, but now it's done sort of in real time. And as we are zooming in, so the way this works is that you have this line, and this table shows all the events to the right of the line, so like afterwards, right after this line, so when the time is bigger. So whenever we move the line, this table is showing things to the right of the line. So if we're here, and then this here is showing us the events in this table, right? So this timeline here corresponds to these times. So as we are moving the time to the right, we move the events this way, right? And so, yeah. So now, if we look at the events, the raw data, nothing's happening, right? Because we didn't do anything yet. But let's do our attack again. Okay, we do our attack again as before. Exit. And what I will do is it will add new events to the log, and we should be able to see those events coming through relatively, quickly within a few minutes. Just wait. And then we should be able to see those events coming through, I hope. Yeah, there it is. Okay, so it's been forwarded, and so we can actually see, okay, here's our event here. Okay, and this is our PsExec rules that are, being passed. We just fold that. That's the full event. And we can see the PsExec lateral movement rules being detected. So what's happening here is that those Sigma events are working on real-time event detection, and looking through the logs and scanning them to see what happens every 2 seconds or so. And then as soon as they find new event messages, they pass them through a Sigma engine and then detect them. So this is how we have real life detections, and they're being forwarded, in sort of almost real time, like within a few minutes, so almost real time. Okay, so what are event traces for Windows? Before we can start to discuss this, I'd like to start off by just firing off a client artifact for track processes. This is just for preparation, so we can talk about how Velociraptor can track processes on the endpoint. So just for this case, we'll do the same thing as we did before. Look at the all, but also add this track processes for Windows, not the basic one, but the full one. And it also uses sysmon to track the processes on the endpoint. So let me just click that. So that's all. We just need to do that so that we can add more context around processes. See, and we've still got more detections happening, that kind of thing. Anyway, let's go back to, so just do that quickly. Same process that we went through before. Okay, so let's talk about event tracing for Windows, ETW. So ETW is actually a really clever architecture in Windows to allow us to get some information about tracing information. So be able to collect a lot of logs inside software. And it's actually a really clever scheme, because normally if you've ever written any code and you try to debug your code by adding more and more logging to your code, then you'll notice that as you add more logging, then the code becomes slower and slower, right? Because you're just printing a lot of stuff all the time, and it becomes a lot less performant. So what we really want is to add a lot of logging, but also to be able to switch it off so that we don't overwhelm the system with too much logs, but be able to really tap into those trace points in a very efficient way. And this is really what event tracing for Windows architecture is all about. We have a whole bunch of providers which are basically programs that want to log, or will offer to log certain things, but they don't actually log anything until someone, a consumer, registers that they're interested in that information, right? So basically it allows software to be written with lots of logging points in the software, but unless someone's really interested in that, nothing happens. It's not expensive, doesn't cost anything, and only when someone's interested in that do they get these events. And so we have the kernel, the event tracing subsystem here is responsible for connecting consumers and providers. But anyway, that's all the detail. It doesn't really matter for what we want to talk about today, other than to say that generally the more ETW sources we will use, the more different types of sources that we use, the more performance impacts that will have, right? So that's basically makes sense, it's logical. If we don't watch an ETW source, then there's no performance impact on the system. Okay, so this is the details of it. And that's what I just said, so we'll just skip that. So there are a whole bunch of different providers. There's like literally thousands of providers, and any software can provide an ATW provider. And it's kind of difficult sometimes to know which is useful and what to do with it. There are some public documented efforts. Let me just show you this website here. Oh, it's probably not here. Yeah. That they try to document a lot of these ETW sources, and so it's actually a really, really good source if you're going to do a lot of ETW work to look at, just different ones, just in random, and you'll see that the type of events that they can generate and that kind of thing. So there's a lot of information there. So what we try to do in Velociraptor is we want to create an ETW model that people can use to write rules. And obviously we're not going to be able to access all the ETW sources, but we'll have a good selection of useful ETW sources, and then be able to have people write rules against that, so that we can, so it makes it a little bit easier to write rules, and then we can document in the website exactly what kind of events that these sources can provide for us. And so we can use them reliably for Sigma detection. So that's kind of the point, to create some sort of a resource that we can use. So let's go back to our website here and look at the ETW base for Windows. And we've got a few different event sources like DNS and the kernel file, the file kernel processes, sysmon, that kind of thing. And so we can access those events that way. And if we open any of those, then you'll see that there is a query there. It looks pretty scary. Don't worry too much about it. This is just how it works. But down here, you'll see that there are some sample events. So for example, if we were to listen to this log source here, Windows kernel, in our Sigma rule, then we will be able to get information about file writes, whenever someone writes a file, whenever someone reads a file, whenever someone closes a file, release a file, that kind of thing, create a file, right? Registry keys, create processes, these kind of things, send TCP sockets, these kind of things. So that already is like super useful. For example, here we can tell when a process is able to access, the network or call another IP or whatever, right? So we basically have a lot of information here given from this ETW source, so we can write a lot of rules against it. So this is what it's for, right? And as before, this is how we would access it with this log source, right? Okay, so as it is before, we don't really care too much about the details of ETW, other than that we can use it, and it's not really a log in the sense that nothing's written to disk, right? So the attacker can delete the log files. It doesn't matter, because we don't really use the log files in this model. We actually get the events directly from the kernel. Okay, and we can enrich these events with external information like the process tracker. That's why I got you to enable that before. And we can do, and Velociraptor actually does a lot of post-processing from the ETW sources. So the ETW sources are not always super useful, because they require a lot of post-processing and state preserving and all kinds of stuff. So Velociraptor does a lot of work in making those useful, and also and then the project site gives us all the samples of the sample the sample events that we get. Okay, so let's see how we can develop Sigma rules with the ETW model. So unlike before, when we just did our developed our model, because remember how before, when we developed our model, we just kind of went into our notebook, had a bit of a play, and then just kind of like we could play around with the Sigma rule, right, and then just keep seeing whether we could detect it or not, right? Like, so if we change this to EID2, or like, oh well, it's not going to detect anything, right? And it was relatively quick. Well, it's still going through a lot of rows. We could, clear the log files, clear it, so make it like less, less busy. So we could play around with it, right? And kind of iterate through that. But that's not really possible with ETW because there's nothing written on the disk, right? So we're not really going back to the same events. Every time we write the detection and try and test it, we have to run this attack all the time, right? Because there are live rules and now live events. So that makes it difficult to really develop it. We need to simulate the attack on a real system like on this Windows machine. Then we need to play around with our rule and then replay it and then reiterate and replay and reiterate. And we never really exactly know whether the same events was generated or not. We just don't know, right? So it actually makes it very difficult to develop rules on a live, system. So, and then sometimes it's actually difficult to simulate a specific attack. I mean, in this case, we're running PsExec. It's pretty easy for this workshop, but, sometimes to do a full attack is complicated. You need to have the system all set up, ready for it. Maybe you have to install some software, maybe you have to add some patch, whatever, like different things. And so it's sometimes difficult to actually run the attack on a system that you don't necessarily want to develop your attacks on, your rules on. So what we actually do when we develop these kind of rules generally is we try and have a detection development workflow. And this is what we generally try and do as much as possible, right? We don't really develop the Sigma rules on the target system very often, right? Most of the time what we want to do is we want to actually record the log source, record the data as a raw data, right? And then when we develop, we replay that recorded data with our Sigma rules into the Sigma engine, right? And that allows us to quickly iterate because we're just playing back a file into a rule and we get a result, right? So we can do that quickly. It takes milliseconds. We do it really fast until we get our rules just right. And then once we get our rules just right, then we can use those rules in real life, in detection mode, when we run the real event source through the engine and the rules. So the idea is to basically insert ourselves into this and kind of mock out those log sources, to write them to a file and then play on and then develop using that file. So we're going to do this process here just to show you like the usual process of how to do this. So first step is to actually capture the attack, right? So in this case, we're going to do our same kind of attack as before, but what we're going to do is we're going to use this ETW based capture test set artifact. So all that does is it captures the event logs from this provider, just copies it to a file, right? So we're going to copy that guy and go over here and let's make another VQL cell up here. Okay, so this just basically captures all the events. We're going to play with the file provider here because we're going to look at like some files. So this is let's go back to the top. So this is this one, right? So this is the one. These are the type of events that we expect to get, file open, create new file, that kind of thing. And so you can see that we want to look for when new files are created, right? So, and we'll have a file name here, field, and some process info and that kind of thing. So what we want to do is actually go back and we're going to just see where any of those fields, anywhere in the event data, is going to mention this PsExec SVC binary, because we're just doing like a quick filter just because we don't want to see like thousands of file events. We are only really interested in certain ones right now for this exercise. So we're going to do this query, and so that will basically go through and use the exact same log source that is used in the Sigma rule and just monitor it. But because this is an event monitor, it just keeps running, right? Because it constantly feeds data from that. So event queries never terminate. They just constantly feed data. So whilst this is running, right, it's just watching for events, right? And then we're going to do our attack like we did before. Exit. Okay. And after a few seconds, we should be able to see those events captured, right? So let's just wait a sec. Okay, so we've got some events, right? So we'll just click stop. That will stop the query. And so we'll see our events that we captured, right? So these are the raw events that we're getting from the system, right? So the raw events, that's what it looks like, right? So we are looking for this PsExec, you know, a service that we're going to write, that is written, and you know, and then the process that writes it, and that kind of thing. So these are the raw data, right? So let's go back to our exercise. Okay, so we just captured the test set. So now we actually can use that to develop new Sigma rules, new Sigma detections against the file that we're just replaying through the engine quickly, so we can quickly iterate quickly. Okay, so let's see how that process pans out. So we are back here. So we have, you know, captured some data. We have 104 rows. Some of them may be relevant, some not. I mean, it's just anything that has the word PsExec SVC in the event somewhere. All right, so what we're going to do is we're going to click download JSON. That's going to download this data as a JSON file. And let's just rename that so we can remember what it's about. Okay, so we're just going to rename that JSON file. And we're going to call it, what was I supposed to call it? Let me just see. Test.json, okay, whatever. We'll call it test.json. Rename test.json, whatever, right? And if you open it in Notepad, then you'll see that basically it's a JSON file and it's got one line per event, right? And then each line has, you know, exactly what we've seen here, just a raw event in it. You know, it's got all the fields, timestamp, system, blah, blah, blah. So that's all it is, right? We're just kind of recording that event. And remember, we're only doing this because the ETW sources are never written down. They're live sources. So we have to record them so we can iterate over it. Okay, and then again, and then we can basically replay them into the same ETW detection. And again, you might want to add that detection. Okay, let's copy that rule back to our notebook. Copy. And then we'll go back to our notebook here. Oops. Okay, and let's add another cell. And so just so we can see it. So this rule basically is similar kind of rule that we had before, right? So we're just going to develop it. But the difference is that what we're doing is we're replaying it on the JSON file that we collected earlier. So if we run that through the detection, then we are able to replay the test set on that detection that we had earlier. Now when we replay the rule, by default, this shows us the match object. So that helps us to debug the way that we are writing our Sigma rules. You can see that we have, and we did match, this event matches, and then this field, selection event type, is true, system.event type. Okay, and we look at system, event type, create new file. Okay, and then event data. So we can actually get a good idea from, you know, before, when we look at our raw data, we can see what kind of, you know, we want to create a new file and we want to match it on the file name. So we can see when we replay it, we are picking this field and matching on the file name, and then this is the condition. So the condition is true because this and this is true, and so we have a detection. But we can play with that, and then iterate through very quickly. So for example, like, if we set this, then it won't match, right? Then we can edit it, and it can, actually, that was a bit wrong. Then it matches because regexes are case insensitive, and so on. So we can basically iterate through that quickly. And that's the general process. We capture the data, and then we develop our Sigma rules on the captured data, on the simulation, from the attack simulation, and then we can actually collect the emulated attack remotely as well. So if we have a different platform that maybe we can't run Velociraptor on, but we can get event sources from, then we can collect that, and then we can iteratively develop that. And that's really important, particularly for that engineering part of detection engineering, where we have to test the detections. We have to make sure that we write tests into our procedures to ensure that there's no regression. So what could go wrong once we have developed detections that work really well in the lab? How do we know that they're actually going to work in the field, for real attack detection, right? So what could happen? For example, like a problem that could happen is that maybe the sensors stop forwarding a particular event type. Someone introduces a kind of configuration change, and suddenly we're not forwarding those log files anymore, or we're not forwarding, or someone changed the policy and suddenly we don't have certain fields in the event. So that actually is a very common problem and happens all the time, because if we have a bunch of detections we assume are going to work, and then suddenly we don't get those events. How do we know? So we have to introduce tests into the environment to be able to know immediately as soon as a configuration change maybe removes one of the collected event types, or maybe the rules are not applied on certain events. And then we can test that by, again, testing against mocked out event sources like we do here, and then just update the events and update the rules. Maybe we can capture more representative events from real life attack simulations. So it's a process. We keep iterating through that and applying tests and making some automated tests. For automated tests are essential. We make sure that event types are generated on the platform. Maybe we run this capture test set, and then make sure that we can generate that we are actually getting these fields that we are supposed to be getting. Right? You can run a program and then see whether you can see the program in the captured event set, and then make sure that the rules are applied to it. So this is just a word on testing and going back to this engineering approach. Okay, so let's recap. So we've looked at event tracing for Windows, and it's actually really useful low-level functionality. We can write very powerful detections, and in the next section we're going to see how to enrich these events with more endpoint state information. So let's talk about how we can enrich data or events from the endpoint by adding more information about things, right? So we've already seen how enrichment works, because we can see that Sysmon added that product attribute from the binary itself. That was an example of enrichment, right? How can we make it better by enriching the events? So far we only applied the detection on event logs, and the problem with event logs is that they're inherently historical. So by the time we go back to what happened to the system, the event log told us what happened in the history, right? Like a day ago, an hour ago, maybe a minute ago, but they don't tell us what happened right now. So a lot of the time the system's already evolved quickly, and so we can't really go and get more information about it because the things have changed. Processes have stopped, files have been removed, that sort of thing. So So with live detection, we have the opportunity to look at other parts of the system because we're quick enough to be able to get this ephemeral information. And so we can actually collect additional context around the events that we normally wouldn't collect with just event logs. And this is really important because a lot of the time the SOC relies on detection response loop, right? So they get a detection, it's forwarded through the pipeline, and they see it, and then they go back to the endpoint to get more information. But by the time they do that, that can be hours, days, minutes, even minutes is still not great to retrieve more context out of the endpoint so that we can see whether it's a false positive or a serious escalation. So because we have direct enrichment, we can actually enrich the data in the Sigma detection itself. The detection engine itself can add additional data to the detection to be able to get that additional context. So the Velociraptor Sigma engine extends the Sigma standard to allow for enrichment. And there's two types of enrichment. There's pre-evaluation enrichment and post-evaluation enrichment. And I'm just going to give you a quick example of each and show you how it can be very useful. So before evaluating the Sigma rule, Velociraptor Sigma engine can transform the original event using VQL function, and that's pre-evaluation. So we do that before they evaluate it, and that allows us to get more information from the system so that the Sigma rule can make a better decision about whether this rule matches or not, in addition to just the event that we are getting from the ETW system or whatever, right? And so in this case, for example, we can add a call chain. Call chain is really important because it shows us the full call chain of all the processes that were used to execute that program, right? And the way we know this is because Velociraptor has something called a process tracker, which keeps track of process lineage, like parent-child relationship, basically. And so we can tell which process started which other process. And so that gives us a lot of context about how did this process, get there? Where did it come from? So let's try a detection logic for this attack, the PsExec attack. So we've seen that a file is created in the Windows directory. And again, so far we've gone for the file name, but we've seen in the first part that the file name can easily be changed. So a file name is not great. So we want to maybe look for something that's just a generic process being written, but a lot of processes are written in the Windows directory, right? Because when you do a Windows update, it writes executables there or whatever, right? So it's actually pretty, if we just look for this very generic rule, then it's going to fire all the time. We're never going to be able to escalate from that. So what we really need is something more. So so that's kind of suspicious, but not really. But what if we can also add this condition to say the process that created the file is launched interactively, right? So from that the file got there from a command prompt, because of a command prompt. And if this happens, then that's suspicious because it means that a command prompt created that process, right? So let's try this detection logic. All right, so what we've got here is a Sigma rule, okay? And this Sigma rule is saying, okay, we're creating a new file, so we want to know about that, and the file name is in the Windows directory, but it came from a command prompt or PowerShell somewhere on the call chain. So someone has deliberately done this. Now normally you wouldn't expect files to be written to the Windows directory from the command shell because normally it's like a Windows update process or something like that. So it's nothing to do with an interactive like command shell. So that is like, that's going to be our detection. Again, we don't know if it's, is a really good detection, but it's an idea, a detection idea. So how do we actually get this? So we have a call chain. So Sysmon gives us the parent, right? So we have a parent process, but it turns out that's not really enough, right? Because if we look at our, so let's look at the example. So what we're going to do here is just use the /s. This is this attack, and when this happens, this PsExec is going to write directly to the Windows system directory. And if we look at the event log, right, there we go, then we will see that, whoops, what happened here? Okay, look over here. So we'll see that sysmon is recording this one. So we got PsExec was written, and we will see that it tells us, you know, things about the parent image, services.exe, no, file created, that's what we're looking for, file created. So who wrote this file, and we can see that the image, the thing that wrote it, is psexec.exe. So we don't know if this is running interactively or not, and again, the file name doesn't mean anything, can be changed. So it's not enough, right? Because we don't know how this program got there. Who writes to that? Who created this file, this program? But that's not enough. We want to know who actually launched that program, like, you know, who is the grandparent of this file, right? So this is the parent of the file, but the grandparent, where did this come from again? And that is not recorded by sysmon because, of course, you know, it's just too limited. Like, you know, who would be the great-grandparents or the great-great-grandparents of the process? So, you know, we really need the full call chain here. So this is why we want to look at the full call chain, which is not provided by sysmon, right? So it's not in the event. It has to be really figured out from the process itself. And we do this by using this pre-evaluation clause here. So let's give that a shot. So we're going to actually do this one on the real system, right? So on the real system, we can't really do it on a captured test set because we haven't captured it yet. So let's create a new cell and paste this thing in there. So this is our rule, right? And then we're going to run it. And then over here, we're going to do our attack here. Same thing, okay? And just wait a sec. It's still, you know, reading the data and refreshing the notebook. Okay, and then we'll see a detection. So there's a stop once we get the detection. Okay, so the detection happened because the call chain. So you can see that this enrichment that we've got here, what's happening here, this is a VQL function that is run. Okay, and what we do is we take the event, the whole event, and give it to this is a lambda function in VQL, and what it does is it adds another field to the event data. So if we look at the event data here, let's look at the row. Close some of these. The row event. Yeah. So this is the row event, right? That's passed through, and you can see there is an event data field, and then what we do is we add another field. This adds another field called call chain, and it's calling a VQL function to build up the call chain. So this is the names of all the processes that are, or the executables along the parent path relationship. And so we can see that this call chain started from Explorer because this is a login session, and then we have the command shell because this is where I'm running from. And then I ran psexec.exe from the downloads folder, right? And then that process actually wrote this file in the Windows directory. Super suspicious because it's interactive, right? So, and then if I look at the data that's passed, then you know that this is the process that wrote it, right? So. So we can see here that we're getting the full command call chain, but the sysmon is only giving us the parent. That's not enough. By getting the grandparent, we get more of a context. This is really important, like on Linux machines, you know, when someone logs in over SSH, these kind of things. So you can actually see like a full like an SSH bash shell is not the same as a login bash shell, you know, it's not the same as maybe an interactive bash shell. So we've got a lot more context this way. Oh, where is it? Okay, so that's how we can enrich data with more information with endpoint state. Just get data from the endpoint state. We can add any kind of data that we want. We can add things from files, from registry keys, anything like that. But in pre-evaluation, this data is added before the rules match. So that means that it can be expensive because we actually do this every single time the event is generated. So in this case, every single time a file is written, we end up calling this, you know, this call chain. It just happens that this is actually a really cheap operation in Velociraptor, the call chain. So it doesn't matter too much because it doesn't cost a lot, but it can have a significant performance impact here, because even those events that don't match, like any file that's written, we are going to call this anywhere, right? So it's a pre-processing, pre-enrichment. It's in pre-evaluation enrichment. So before we even evaluate it, we enrich the data. So that's not good, right? So sometimes we want to evaluate things post-evaluation. Post-evaluation happens only on rules that match. And then what we want to do is add more context so the analyst can see the data, this context, and evaluate whether this rule was false positive or not. But the rules already matched, so it's post-evaluation, right? So it only happens when the rule fires. As long as we can write our rule to be fairly targeted, then we can add the enrichment. So there's like pros and cons here, right? So for post-evaluation. So what we're going to do here is, in this case, we're going to add some post-evaluation data here, and that happens after the rule matched. So let's do that. So we can leave that the same, that's fine. And then we can add post-evaluation. So let's do that again. Okay, we'll run the attack again. All right, and just wait a little while till we get the event through. Okay, there it is, we'll stop. And what happens here is that the event is firing just like before, so the post-evaluation doesn't matter, doesn't change the event. So let me just clear off some of these unnecessary fields. Okay. Yep, and I'm going to show the original event and just the enrichment. All right, so actually we don't even care about the details either. So that's the original event, and then the enrichment. So this enrichment happens after the rule evaluated. After the rule evaluated, so we basically parsing the PE file from the system. Right, so we remember that if the file is changed or modified, we can see the version information, resources here, version information. So this is the same thing that, Sysmon was showing us, right? Post match. But we can't match on it because this is happening post match, right? So we're just enriching with this data. But it actually does all of these other checks, which are also important. For example, we can see whether it's signed, right? Whether the signature is trusted, whether the certificates and so on, it's actually trusted. The hash, matches the signature, because so that maybe it hasn't been modified, and so on. So because it's not modified, right? So this one, and then the imp hash, which is the import table hash. Okay, so we get all the imports, and we can sometimes use the import table as a signature, on the system, because if it's trusted, so it cannot be changed. and so you can't really have the import table changed and the signature matching at the same time. Okay, and so we've got more of the information here, so the analyst can look at that data and decide whether this is a false positive or not, or a normal one. So this is an example of a post detection enrichment. Oh, there we go. Okay, post detection enrichment. Okay, so we've seen how that is done. All right, so we've got all of these tools for making better detection. So how can we think of making better detection for PsExec, right? Knowing all the things that could be changed. So the first step would be to understand the attack really well, to understand what is going on here and what are the things that we could use to detect it. So we've already seen us going through the different parts of the attack. We've seen that we have the original tool executed, and that happens on the attacker's machine. So maybe we can detect something about the actual original tool that's launched. We've seen that there is a EULA registry key. Maybe we can use that. We've seen that we created a file into the Windows directory. We've talked about that. A service is created. Maybe we can somehow trigger on that creation. Service starting, we somehow can trigger on that. We've got a command shell spawning from the service, like that could be something interesting to look at. And we've got a system user, command shell running as system user, so that also could be used for detection. So there's a lot of possibilities here for detecting this attack sequence. All right, but then there's a lot of ways that we can bypass this. If we're looking for process names, it's very easy to change them. We can change binaries, we can change EULA, version information, we can change all of these registry keys, we can change service names. What we try and do is distill the things that are difficult to change about this attack. The thing that how this attack works is that we copy a file to the Windows directory because we are installing a service, and then the service is running. And so because the service is started, the shell is going to run as a system. That's kind of the point of the attack. So that's unusual, and you can't change it because that's really what the attack is. So that could be a good signal. So there's a difference between just having lots of signals and having good signals that are difficult to change. All right, so let's capture some test set, but this time we're going to look at writing a very specific file detection for this attack, but we're gonna make it a little bit hard. Whereas before we looked for PsExec, file, then now we're going to basically look for we know that's going to be changed, right? So we're going to change it to something fairly unique, like testme.exe, and then we're going to look for any file events that mention that file name, and we can see how we can do this detection. All right, so let's copy that, and let's start to collect. We'll just make another one, doesn't matter. Okay, and so what this one does is it's going to look for all size file events, and we're just capturing them as we did before, but this time we're really only looking for a fairly unique name, so just that name that we're going to use. So we're going to run that. Okay, and then it's going to basically sit here and watch for the file events. And here we're going to use -r test me. So we know that when we use the -r flag, it copies a file called testme.exe, and it works the same. It's fine, but now we're going to see what kind of events that we can attribute uniquely to that file. So we collected some events, so let's stop it. That's great. Okay, so now let's see exactly how this attack unravels, right, in terms of that particular file name and that particular provider. So the first thing that we can see is that we are opening this file, and you can see how this is actually an admin share. So normally this attack is a lateral movement attack. So we have two ends. There is the attacker machine, and then there is the victim machine, and we are attacking across the network. And so you can see that the attacker machine accesses the remote machine over the network, over an admin share, the admin share, right? And that's how it writes the file on the admin share across the network. So this is coming from the attacker's machine, right? Attacker's machine, this is the PsExec binary, and it's writing across the admin share, right? So that is already kind of interesting. And then immediately we're seeing the other side, because this is happening like locally, so we can see both sides at the same time. And immediately we are seeing this is the victim machine. The file will be created in this directory, C Windows test me, but who is creating that? System. So the kernel is writing this because this is happening across the network, right? Our remote shell across the network. So because it's written to the admin share, and then the kernel, services that admin share and writes the file down. So this end happens on the victim machine, right? So we can detect that. There's a whole bunch of creating new files and writing files, and this is happening here. Okay, and then again, it's all done by system because it's done over the network. And then we're creating the file. This is the victim end, doing all the same thing, creating the name and all that. And then what do? And then we're deleting it. Then the file is being deleted, okay, from the admin share, right? And then over here, we also have a very interesting thing. We have file open, okay, oops. But so this file is opened again, but who is opening it? Okay, it's services.exe. So the service control manager is actually opening the file. Why? Because this is a service file that's running, right? So the sequence is about running the service, right? So the service control manager opens that file. So let's have a look and summarize this access pattern that we are seeing to this file, like what's going on with it. Okay, so first of all, we can see the two halves, right? This is the attacker machine, and this is the victim machine, so two halves. So there's different point of views here, and we're just seeing them together because we're doing it locally, but you would normally see this on the victim. You would see this sequence, right? File is created by the system user, and then it's opened by the services.exe, and then it's deleted by the system user, right? And then on the attacker machine, we will see file is created on a network share by PsExec.exe, right? And then the file will be deleted by the network share. So that's the file interactions across the share. So there's two halves here, and we can capture two sides of the attack. Now, each action on its own, not super unique, right? Like when you think about it, files written by system happens all the time. Files opened by services, I mean, every service literally is opening in the service file, so it's really not that unusual. And files deleted by system, maybe that's a little bit unusual, but it happens during upgrades and things like that, so it's not that unusual. So, but let's detect all of these attacks, right? So we could just copy these guys, these rules. Okay, let's create another VQL cell. Okay, and let's have a look at this detection. The first detection, file open, when the file name starts with Windows, ends with exe, okay, and then the process name contains system, so that is when system is opening this file, right? So that's the first detection. And then the second detection is when services.exe reads this file, okay, and then the third detection is the file is deleted, right? So we have three things, right? And then we're going to replay these detections from the JSON file, but first we have to save the JSON file, right? So let's do that. It's this one, download JSON. So this is the event data that we had before, so we'll save it, and then let's rename it to what do we call it last time? Test Okay, so let's go over here. Okay, so we're going to just run these detections again against the replay file, and okay, it's fired, you know, a few times, and we can see here the matches at the particular detection. So let's have a look at the first one. Executable is written in Windows, and we can see that the file, it's a file open. Okay, and somewhere in Windows directory by system. The second type of let's just pull that. Second type of alert is file in Windows read by services.exe. So again, we have services.exe is the process, and it's reading the file name, which is in the Windows directory. So that's great. And then the last type of event is a file in Windows deleted by the system process. Okay, and then we can see that there's a file delete operation, and it happens by the system user, so the system user is deleting it. So so we are seeing all of these, you know, events firing with our replay. So that's great, but we can't really use that as a detection because all of these are fairly common. They just happen all the time, and it's just going to make far too many false positives, right? So what we really want to do, we see the first rule trigger, and also each rule triggers multiple times. So if we just had all of these rules, we would get 9 different alerts. Each of them is pretty low quality, but they are triggered 9 times. And so to solve this problem, it's not just the event itself that is important, it's the combination of these events that actually matters. So the attack is described as a sequence of steps. What happens in the attack is one thing happens, and then another thing happens, and then another thing happens. So each of those things is not necessarily unique, but the combination of those things in order within a short succession, so it happens quickly, that's actually very important. And so this is what we want to do, is we want to correlate the rules. Like up until now, we were just grepping the rules. So if a rule matched, it was a hit. That's it, right? But what we want to do now is correlate across multiple events across time. And this is called a sigma correlation rule. So here, let me just open that correlation rule, right? So this is explaining all about the different kinds of correlations. We have a number of different types of correlations defined in sigma. And so sigma rules can define a correlation. Let's have a look at what types of correlation we can do. So we can correlate across an event count. We can see how many times a rule fires within a timestamp. That's useful, for instance, to say like, 10 failed logins in 2 seconds, that kind of thing. So each failed login is an event, but each failed login in itself is not super noisy. It's not really that valuable, but if someone's trying 10 of them within that 1 second, that's a brute force attack. That means something. So it's just how many times did we do it within the time span. And value count is checking that a field appears more often within the timestamp. For example, someone is logging into this user account from multiple IP addresses, and let's say within a few seconds. That is a brute force attack to try and defeat, lockout detection type thing. Or temporal, which means all of these events will fire within this time stamp and this time span. This is what we are looking at here, right? The temporal detection. So let's have a look at what that looks like, what kind of sigma rule it looks like. So a sigma rule, there's a correlation rule, is a little bit different because it doesn't have a detection clause, it has a correlation clause here. Then we have the type, temporal detection, and then the rules. And what we're doing here is we're referring to other rules, and we're saying these rules all have to fire within 100 seconds so that we could, get, so that would be considered a hit. And then, of course, Velociraptor allows us to do enrichments, and in fact, Velociraptor allows us to report all of these particular matches because we're collecting all the hits. All right, so let's replace this detection with this one. Copy, and again the same kind of thing. Let's create another cell here. Fine. So it's the same kind of thing, except that the difference is that now we're going to name each rule so that we can refer to it with the name column. So there's a name. So these are the same thing, except we just gave them a name. And then the correlation rule is here, is actually detecting all of these rules, right? And then we have the enrichment type thing. So let's see what happens here. So we're running this rule again on the replayed, and we can see all the columns that would be shown with the real collection. So let me just clean it up a bit. Just remove some of those fields that don't matter too much. Let's just clean it up, and we can see that we have the enrichment that we have calculated before, and the enrichment actually labels each hit that was made by each rule within the correlation. So we can see that here we have one rule, the first rule, and then the second rule, and the third rule, and only when all three rules have matched, then this sequence is detected, and we're able to identify the sequence. Okay, and let's try now to change the rule so that we could apply it to the real ETW source. So we're going to comment out this, and when we're ready, we'll actually go and fire off the real rule. So now that we fired it off, it will just sit there and wait for new events, so that we can go over here, generate the attack as before, and then don't forget to exit. And in a short time, we should hope to see that rule fire. There it is. Okay, so we'll just stop it, and you can see again the rule. This is now in real life. This is the detection that happened for real, and we can see the three rules that fired. If we just clear off all of these ones, then we can see that the enrichment is showing us the different rules that fired. This is the first rule, this is the second rule, and so on. So you can see that we didn't rely on the name of the binary, and we didn't really rely on any properties of the binary that could be changed. We just relied on patterns of behavior. That's what correlation allows us to do, is to rely on patterns of behavior and combine low fidelity rules. Alright, so let's look at how to improve Sigma detection. So the first thing that we saw is we can enrich the events with endpoint state, and it gives us more valuable context. And it helps us to preserve ephemeral information that will disappear, and cut down our response loop, because we get that information that will help us to triage these events quickly. And then we looked at this example as a full process chain enrichment, which is important to get that information to add to the evaluation of the event. But it can be expensive, especially if we're doing a lot of these enrichment server-side. Like if we're doing a lot of these full process cold chain enrichment, server-side is actually expensive. And also it can be expensive, on the endpoint if you're reading lots of files and that kind of thing. So we can split them into those enrichments that are necessary for detection, and for those that are, necessary for assessment. And then we saw how we can use correlation across events to help us create stronger detections. So this is the workshop about detection. And what have we learned? So detection engineering, we've only just scratched the surface of detection engineering. It's more than just typing queries. It's thinking about improving the odds of detection strategically. So we are now looking at how to make this reliable, how to make this robust, and how to test it. So how do we test it in an ongoing way so we can detect any breakages? How can we adapt to new subversion techniques? How can we adapt our detections? But don't get me wrong, what we said here isn't, I never went to say that we have to be perfect. We don't have to be perfect. We can just be, perfection is the enemy of the good. It's okay to write like some low-hanging fruit, simple detections. Just because an attacker can subvert it doesn't mean that they will. That helps, right? So it's better to have simple detections out there than to have, than to take a very long time to have no detections until they're perfect and can think of all the different subversion techniques. So they can cover off on each other as well. Like sometimes, when someone have to modify the binary, then it's no longer signed. So that's another signal, or the signature is there, but it's wrong, or whatever. So we can have different kinds of detections. Like if we're running an unsigned binary, maybe that is a detection in itself, right? And that can add off. So sometimes we can force attackers that by trying to subvert a detection, they're actually triggering a different detection. And then we can cover off on each other. So it makes it very difficult to bypass. But the most important thing to remember, you only really need one rule for us to be able to catch the adversary. When they're doing their full attack chain, there's lots of steps in our attack chain. And if we miss a lot of these steps, that's okay, as long as we can catch one of those steps. And it might be, it might be just a very simple attack. We just need to get that one detection and we can kill the entire attack chain. So it's actually important to have lots of different detections and run them at scale. So hopefully that explained a little bit of how detections and Sigma rules work in Velociraptor and in other systems. And if you have any other questions, you can send an email or jump on the Discord and talk with us, or play around with Velociraptor. So thanks.